Hello, welcome everybody this afternoon in Europe to the 7th installment of this MIGGEN series, which brings together young people, young researchers in age or in heart to facilitate or to create a few hours where we can interact scientifically. That's very much in the spirit of CCAM. In those times where still traveling and having the possibility to meet is not easy for everybody yet. This series, as you know, for those who are new, we bring together people that lecturer and also participants that are more experienced together with other ones who are at an earlier stage in their careers to exchange scientific interest, information and ideas around different topics in modeling and simulation. The topic of today, it's simulating non-equilibrium phenomena and rare events. And as usual, we organize this event in two parts. There is a first session where we will listen to 3 presentations, one by a more experienced researcher. Today is Tanya Schilling from the University of Freiburg, and 2 younger members of our community, Regis Santé from École des Ponts and Janine Scheer from Johannes Gutenberg in Mainz. And the second part will be then we will move to using Gather to a virtual poster session where I think today we have 10 posters presented by other participants. And then this is also an opportunity for everybody to continue the discussions with the speakers that we will have had, and then also to interact with poster presenters and with the rest of attendees. To access the Gather session, you need to be registered. Those who are attending and have not registered, there is the possibility to email us, and then we can send you the link if you want to join also for this second part. Now, before we start the event today, let me, I wanted to make a small, as usual, just a small presentation with practical information. So being online, I think that by now we are all of us are mostly used on how to behave, but just it's a bit of an etiquette on how to interact during the next couple of hours. The meeting, with the exception of the first talk, will be recorded and will be available on the YouTube channel and on our website. Also, the presentation, the first presentation, will be available as a PDF if you want to come back to it. The interaction during this, so the video, participants, you cannot use to activate your video and also the chat, so that then all the interaction during this first part will take place using the Q&A facility that you have access to on Zoom. So anything you want to comment or transmit, you can do that through this Q&A. Now, the first lecture, the one delivered by Tanya, which is longer, because of that, I will allow that you write, you can write questions during her presentation, and then I will take care of passing the question to her as she explains her lecture, her lecture develops. And then at the end of her presentation, then there is an extended Q&A session. And then in that part, it's enough that you indicate that you want to ask a question. There is no need for you to write the whole question. And then we will allow your mic, we will open your mic so that then you can directly ask the question. And I think this will facilitate more interactive discussion with Tanya. And if there is a question that is more elaborate or has a follow-up, you can then have a more appropriate discussion or conversation. In the other 2 presentations, because they are shorter, I will not take questions during the presentation itself. And then at the end of the presentations, we have again this Q&A where you can indicate you want to ask the question, then we unmute you, and then you can just talk directly with the speakers. Before we move on, a couple of, where I am, yeah, here. I wanted to talk, to at least to advertise two other type of online events that will be happening during the next month. Beyond the Mixed Gen series, we also organize periodically the Marianne Man-Side conversational series. That's something that we do together with Marvel, a Swiss initiative. And here the next Marianne Man-Side event will happen in May the 5th. So that's next week. In this case, we will, I mean, this series aims at addressing aspects that are relevant, or the impact that computational modeling has beyond our more academic circles. So in this case, we invite Eric Beamer, who has been leading and creating a software company. So he has a lot of experience and insight in the development of modeling, but also in the interaction with companies and industry. So I think that will be an interesting topic for a conversation. This is a hybrid event, will happen physically in Lausanne, but will be also performed, streamed, and therefore you can participate remotely. And also again, as for all this series, previous SICA Marvel lectures and Marianne Man-Side events are available online, on our website if you want to check previous ones. And then if you find this interesting, you are invited to attend next week. And also the MixGen series happens periodically every month. The next installment will take place beginning of June instead of the end of the May, but it will be June 9th. In this case, the topic will be about electronic energies beyond density functional theory. And the more experienced lecturer will be Lucia Reining from the École Polytechnique. So again, if you are interested, you can register as you have done for this one, and just also enjoy an afternoon around density functional theory and beyond. And also, as I mentioned earlier, previous sessions are available on our website. And also, if you go to YouTube in the SICAM channel, you can also access the corresponding videos there. Let me finish by saying that you can also register to our webinar mailing list. That's something, if you go into our website on the page of the MixGen, for example, there is a possibility to register, and in that way you will receive periodically the announcements of this online events and other online events that will happen in the future. And if you also follow us on Twitter at SICAM events, then I mean, we also advertise, communicate these events through that channel. So that's an easy way for you to keep updated into upcoming online and hybrid events. So I'll finish here this presentation. So I now can move to science. So the first talk today will be given by Régis Santet from the École de Pont. He will be talking about unbiased sampling of HMC schemes for non-separable Hamiltonian systems. So Régis, now the floor is yours.
Yeah, thank you very much. All right. So thanks to the organizers for having me present my my first work. So I've changed a bit the title from what I decided to put on the SICAM website. But okay, so I'm a first-year PhD student in Paris at École des Ponts and INRIA Paris, and my supervisors are Gabriel Stolz and Tony Lelièvre. And mainly what I will talk about is the use of Monte Carlo and Markov chain Monte Carlo and Metropolis schemes for Langevin-like dynamics. So you'll see I have a specific case in mind, which I will detail. And you see there is I mainly focus on rare events. I'll mainly be at equilibrium, but this is a future work in my PhD pursue. Okay, so thanks to Tanya for having those reminders of basic statistical physics, because this will go smoothly now. What I want to compute is an unbiased estimation of an observable, which I call f here, which is a function of my position. For example, I have a system with many particles, or maybe only one particle here. And I have a configurational space, which I call x here. And basically, this computation that I want is the expectation of this observable under some invariant measures, which is for us the usual Boltzmann-Gibbs measure, exponential minus beta v, where v is the potential and beta is the inverse temperature. And I want to use this estimator here to compute this quantity. So what I want to do is to create a Markov chain. So this is Qi here. And this is like samples from the trajectory, for example. And I want this Markov chain to have pi as its invariant measure. And it is quite difficult to have sometimes it is quite difficult to have an idea of this quantity because, well, potentials can exhibit a lot of issues. We can have a lot of issues when computing those trajectories. For example, it's hard to explore anisotropic potentials, or some dynamics are metastable. So there are also many ways to help the system actually go to unseen places, or to go to cross energy barriers, for example. And one solution that I have in mind is I want to introduce diffusion coefficient, which is position dependent. So now usually when we talk about the overdamped Langevin dynamics, what we have is the minus gradient of V here as for the drift term, and some noise which has like the square root of 2, and here beta, so that I have the inverse temperature term here. But what I want to introduce is this matrix term here, which is a positive definite symmetric matrix D, and it is position dependent. So really what I have is a multiplicative noise in front of the Brownian motion. And because of this multiplicative noise, I have to adapt a bit my drift term. So I have to put some D here and also another term here, so that in the end, my process still has pi as its invariant measure. So still the Boltzmann-Gibbs measure. And so now the real challenge that I have this overdamped Langevin dynamics, and I want to implement an efficient, unbiased numerical integration. So first, I should actually advocate on why should we use this, on how should we choose actually this diffusion coefficient. So what they use in the Bayesian inference community mainly is computing this inverse of the Hessian of the potential. Now this, for us doing molecular dynamics, this can be a bit too complicated to compute on the fly. And various work suggest instead of having this diffusion coefficient, which is proportional to the exponential beta v times an identity matrix. So in the metastable case, this can help us because when v increases, when the potential energy increases, then so does d. And to illustrate this, I have a simple 1D potential profile here that exhibit two wells. You can think of those two wells corresponding to two metastable configurations. And I've plotted here two trajectories, and those two trajectories can be compared because I started them at the same point and I used the same noise for each of them. And you see here that, for example, when I use like the usual additive noise in front of the Brownian motion, here this is a trajectory in blue, whereas if I use the diffusion coefficient, which is of this form here, then I have this trajectory in red. And whereas if I am at the bottom of one well, then I do not move that much because V is a bit low. But as I try to cross, the potential energy gets higher, then I start to really speed up the pace, and to speed up across this plateau here that I have, so that I can jump from one well to the other more rapidly. Now, it is important to know that this diffusion coefficient can only be known up to a constant. Well, can only be set up to a constant. And if you multiply this diffusion coefficient with a constant that can be as large as you want, actually you will accelerate your convergence towards steady state as fast as you want. So actually, numerically, of course, this is not something which can be done in practice, but in theory, this can be done. So there is some kind of normalization that you have to put for this diffusion coefficient. So here I've chosen one normalization, so actually we can compare those two diffusion coefficients here. But this is like a really tricky question. There's this normalization constraint that you have to keep in mind when you're introducing this diffusion coefficient. So this was more for the metastable case and the sampling of rare events. I have another illustration for the anisotropic case. This I have a 2D, like a really anisotropic 2D potential here. So this is a target measure in white. So this is only on a really thin circle. And my dynamics can be like a bit trapped, because if I go orthogonal to the circle, then I will not actually explore the whole circle. So I can be trapped a lot. And this is not because of energy barriers, but more like entropic barriers. And just to show that having this diffusion coefficient, which is position dependent, it can help to actually explore for a fixed number of iterations. What I really want is to travel all along the circle, right? So I can have the usual diffusion coefficient, like the isotropic diffusion coefficient, which is proportional to the identity matrix, or an anisotropic example that I've chosen here. Really what I do is I am at a point of the circle, or maybe close to the circle. I compute the tangent vector from where I am. And what I want to do is to project back the noise towards the span of this tangent vector, right? So actually the noise helps me to go along and have this, in this way I have the direction. I go along the circle, I try to take into account the geometry really of the potential. So now I have to actually make sure that this diffusion coefficient is invertible. So this is why I have a small parameter here, epsilon here, times the identity matrix, because this projection matrix onto the span of the tangent vector is actually of rank 1 if I am in two dimensions. And this is also why I have this epsilon factor here, because in that manner, those two diffusion coefficients have the same norm. So I can actually compare them. And what I do for this plot is I compute after a fixed number of iterations of my computations, the distance to the target measure, actually to the invariant measure of the angle distribution. Because my target measure has an invariance, a rotation invariance, the angle distribution has to, well, the invariant measure of the angle distribution has to be the uniform distribution on 0 to pi. And I compare here, with respect to the time step that I choose for my numerical simulations, the distance to this invariant distribution between my empirical, the one I compute on the fly. And what I want to compare is actually the two minima of those two curves. So for the blue curve, it's the computation, like the error I do after a fixed number of iterations. With this isotropic diffusion coefficient, and on the green curve here is for this anisotropic diffusion coefficient. And now you see that the two minima here, as those are the ones I want to compare, and you see that I drastically reduce the error while still having the same number of iterations for my numerical simulation. So this can be really advantageous to have this diffusion coefficient here. Also see that the optimal time step for this diffusion coefficient, which is position dependent, you see that it's a bit shifted to the right so that I can allow to have larger time steps. Because actually I project back the noise, my proposals when I integrate my dynamics, actually I can have larger time steps here. But you see that on this plot that I have a compromise between having small time steps and basically the error I do on the distance with respect to the invariant measure is basically scaling as 1 over the square root of the time step in the more like in a continuous setting. And for larger time step, I get like my dynamics get stuck a lot because I cannot move very well. So this has to be a compromise here. But for now that I have advocated my my point of view of introducing this diffusion coefficient, what I really want to do is to have an unbiased estimator of the quantities that I want. And the quantity that I want is an expectation of an observable with respect to the Boltzmann-Gibbs measure. And for that, numerically, I have to implement like a Metropolis Hastings procedure. And with my overdamped Langevin dynamics, basically the natural candidate for that is to have some kind of Euler-Maruyama integration here. But if I do that, then the rejection rates in this Metropolis Hastings procedure here scales, well, not very great. It's as the square root of delta t here, but delta t is the time step that I've chosen. And this is not something that I want, of course, because as I said before, I want to reduce computational time. I want to have larger time steps in a way. So a better choice in that case is to go into the Hamiltonian Monte Carlo setting, which is basically, which is based on the integration of the Langevin dynamics. So I introduce a momentum variable here, and I have kind of Hamilton's equations in this setting, along with an Ornstein-Uhlenbeck process here. And I have to choose the right Hamiltonian so that in the end, I can actually compare this to the overdamped Langevin equations that I had earlier. And for that, I have to choose this Hamiltonian in particular. So it has like the usual form in a way, like this V term here, this potential energy term. But you see here that the kinetic term is coupling the momentum variable along with the position variable. And you see here also that this diffusion coefficient is amounts to using a mass tensor, which is position dependent. And I have this ugly term that I have to add to ensure that because the invariant measure of my process QP is exponential minus beta h now, the marginal in position has to be pi, has to be exponential minus beta v here. And this is why I need to add this ugly term here. But anyway, this works. And in theory, I can compute every term that I have here. So now the Hamiltonian or the generalized Hamiltonian Monte Carlo algorithm reads like this. Just so you know, when using this Hamiltonian in particular, this is known as the Riemann manifold Hamiltonian Monte Carlo. So what I do is I sample the momenta either by integrating the Ornstein-Uhlenbeck process or by direct sampling. It depends on which one which version you choose of the HMC. And then I integrate the Hamiltonian dynamics. But because I have this coupling term here, my Hamiltonian is not separable. And this implies that because I am in this setting, I need to have a numerical scheme which is time reversible and symplectic. I need to, well, usually you would use this velocity-Verlet kind of numerical scheme, but I need to use its generalized version so that I have those two properties here. And this implies that I have to deal with implicit numerical integrations. And so after this integration with the Hamiltonian dynamics, I need to apply, of course, the Metropolis Hastings procedure. And afterwards, in the end, this algorithm as a whole, it has an effective rejection rate as the delta t to the bias we have. So again, one order of magnitude for my time step, which is really good. So now if I just implement that using, for example, for these two implicit steps here, I don't know, maybe Newton's methods or fixed point iteration methods. I have an illustration for a 1D double well confining potential here. And you see that for small time steps, I sample the Boltzmann-Gibbs measure very well. But as the time step increases, you see that I have a lot of bias appearing, right? I do not sample at all the right invariant measure. And this is because of the presence of those implicit methods here. I have some convergence issues and also some numerical reversibility issues. This is because in the continuous setting, of course, this numerical scheme is time reversible, so that if I go from one point to the other and then integrate back, I just stay from where I was. I just stay where I was. But if in practice, those implicit methods, they can have, well, no solutions because I do not converge, or they may have multiple solutions. And if I do not choose a solution which takes into account this numerical reversibility here, then actually my method will not be unbiased. So I have to correct for that. And so basically what we do is a natural way to look at it is that if I have a position in phase space starting from Q0, P0, and I integrate the Hamiltonian dynamics, and if I do not converge, then I just say, okay, I stay where I am, and at the next iteration, maybe I will have another momenta, and I will have another go at it, and maybe this integration will work. Now, if I go to this, if the forward convergence actually does converge to some point in the phase space, then what I want is I want to check if I have numerical reversibility. So what I do is I revert the momenta here and I integrate again the Hamiltonian dynamics. Now, of course, maybe it does not converge. And if it does not converge this time also, I stay where I am. But sometimes I can converge, but maybe I have a lot of solutions starting from this point here. And this means that I do not satisfy, for example, if this is not, I do not arrive back at Q0, P0, I do not check numerical reversibility. And this also implies that I stay in place for my algorithm. And of course, what the real thing that I want is I want to integrate forward, backward, and starting from this point, I go back to where I was. This is the main idea here. And if everything is successful, then I just say I'm integrating, I'm at Q1, P1, and everything goes on. So this is like the adapted version because of those implicit steps we have to take. We have to integrate this, and this is the adapted way we have to deal with it. So this is the result for the same double well potential that I had before. So on the left, it's a sampling using our adaptive algorithms where I need to integrate twice per time step in a way, so that I can check for numerical reversibility. And this on the right is without those checks that I've just showed you. So for small time steps, you do not see any difference really. But for as we increase the time steps, you see that on the right, a lot of bias is appearing, whereas on the left, we still have an unbiased sampling of our Boltzmann-Gibbs measure. So really, the take-home message from this talk is that introducing this position-dependent diffusion can really drastically reduce your error, and it can help accelerate convergence towards steady state. But there is some care is required, right, in these numerical integrations, because if you want to have this you have this non-separable Hamiltonians if you're in this Hamiltonian Monte Carlo setting. So you have to be aware of those issues and maybe to check sometimes that you still have the key properties in order, well, so that you're in the end, you have an unbiased estimation of your observable. And well, the future work for my PhD is actually to adapt this diffusion coefficient implementation towards a higher dimensional case, maybe use the free energy along with the coordinate reaction psi here. So instead of having this exponential beta v, we have the exponential beta f of psi q, which means that we can cross free energy barriers. And this can help also for rare events. And of course, there is an adaptation to the non-equilibrium systems. If F, for example, is a non-gradient force and eta controls the magnitude, then of this force, right? Maybe we can have this overdamped Langevin dynamics with this another term here. And this diffusion coefficient can help us actually compute more efficiently, for example, transport coefficients. So that'd be it. So thank you very much.
Thank you very much, Reggie, for this presentation. We now open the time for these questions and discussion. Remind you that you can simply indicate on the Q&A functionality of Zoom your interest to ask a question, and then we will unmute your microphone, and then you can directly ask Reggie. While we wait, I had a number of curiosities associated to this algorithm. So you said that you have this algorithm that is implicit, and then you discussed this sensitivity to the time step. It's not clear to me to which extent the algorithms that you are using can ensure that you keep the simplicity of the standard Verlet, or they are intrinsically not symplectic, and what you discuss are ways to try to minimize the impact when you integrate the equations.
Yeah, okay. So actually, the generalized Thornberg-Verlet, which I use here, is symplectic. When you just look at it without actually having those, without considering the issues that you have, for example, without those convergence issues and all of that. So it is symplectic because it is a composition of this Euler A and Euler B schemes, which are symplectic. So it's a composition of symplectic integrators. So this makes it symplectic. So in a way, we do not lose that. But of course, and as you point out, it's a really soft spot because it's very hard actually to make sure that we still, for this adapted algorithm that we have here, that we are still having symplecticity, right? Because it's not clear. For example, okay, if we do not have convergence or if we do not have numerical reversibility, then we just stay in place. So we do not need, in the case where we just stay in place, we do not need symplecticity because just staying in place is measure preserving, and measure preserving actually makes sure that we are reversible with respect to the Boltzmann-Gibbs measure. So it's not a problem. But of course, you have to actually explicitly describe the sets on which in the phase space of the points of the phase space, sorry, which actually do converge and has this numerical reversibility thing. And this is something that we are working on right now. It's something we have checked that actually. So it has not been, it's in progress, in preparation, right? It's something that we actually describe. We describe the set on which those, in phase space, those points actually, something is not working or something is working. And for the sets of points in phase space where everything is working, then we actually show that this set is open. Mm-hmm. And because this set is open, we can actually retrieve symplecticity from the usual symplecticity of this generalized Thornberg. But of course, the fact that this set is open is not obvious at all. And we have to work a bit on it.
Okay, thank you. There is a question by Burkhard Dunberg.
Yeah, okay, thank you. Very nice talk. And so I understand correctly, I mean, what you are developing is sort of an enhanced sampling method where you try to get through phase space more efficiently. And I mean, this is an age-old problem, and many people have worked on that with various approaches. And quite typically, what people are very often trying to do is not playing around with the diffusion coefficient as you do, but rather with introducing some sort of biasing potential in order to flatten out the free energy landscape. And there it turns out that when you have more complicated systems, you have sort of a chicken and egg problem because you simply don't know what the potential of mean force is, and therefore these methods are typically sort of iteratively. I mean, when you think of this method by Parinello and company.
Well-tempered metadynamics?
Well-tempered dynamic, exactly. Yeah. Thanks. I was missing the word for the moment. Yes, and so this is iterative, yeah. And I would expect that as soon as you go into more complicated systems with complicated potentials and many degrees of freedom, you will probably run into very, very similar problems, and that and that you might need some sort of self-adapted iterative improvement of your diffusion coefficients as well. Have you already thought along these lines?
Okay, this is not something we work on, but this is definitely something to keep in mind. I think like biasing along on the fly your potential, or having this the different terms actually evolve when you're computing your simulations. Mm-hmm. It has been I think Pierre Montmarché has some works on it from Sorbonne University. And also, yeah, of course, when you're talking, you don't know for sure, when you're in a high dimensional setting, you don't know the potential, right? You just, also even the free energy landscape, you do not know, you just explore it as you go. And basically, this is a bit reminiscent of what they do in this Bayesian inference case. What they do is that as they go, they observe really this. So for us, it's the Hessian of the potential. For them, it's called the observed Fisher information. And this is observed Fisher information, right? So as long as they go, as they add more samples so that they bias as they go, right? So they modify this diffusion coefficient, but we do not actually modify it because, well, for us it's a bit, we know that this overdamped Langevin dynamics, written in this way, it is so that this process has a pi as its invariant measure. And
that's obvious. Yeah.
We have to make sure that if we bias along the way, we have to correct maybe some terms. But yes, this is definitely a way, maybe a way to go is to actually bias as you go. You just change your diffusion coefficient.
Yeah. Yeah, I mean, this iterative adjustment is not, of course, is not for trying to sort of asymptotically satisfy detailed balance or getting your equilibrium distribution right. I mean, that's obvious that this is correct, but just in order to speed it up. So it might initially be still very slow, and the more information you gather, you might be able to sort of boost it more, further and further in terms of speed.
Yeah. So definitely, this is what they do, because sometimes they go in the Bayesian inference community. They go very far. They start very far away from the central point of their distribution that they want the posterior that they want to actually sample. And this definitely having this observed Fisher information metric that they have makes it so that they go very fast. So this is a paper by Girolami and Calderhead where they do that, but mainly in the Bayesian inference community, they do that a lot. And well, in molecular dynamics, if you are interested in having to speed up your computation so that you sample very well your rare events, for example, definitely it's something that you can do. I've not worked at all on it right now.
Okay, thank you.
Thank you very much. There is also a question by Karsten Harman.
Yes, thanks. And thanks for this very nice talk. I have a question regarding the diffusion coefficient that you changed. Do you have some intuition why the speed up by the change of the diffusion coefficient and the Metropolis-Hastings acceptance rule go hand in hand? Because it might happen that you speed up your sampling just by changing the diffusion coefficient, but the acceptance step completely eats up the speed up because you reject too often. So why does this work so well together?
So yeah, this is a good question, because if you're using, if you actually just have this Euler-Maruyama approach for the overdamped Langevin dynamics, really having this, usually you have this Metropolis adjusted Langevin algorithm. So if you do not have, if you choose D, which is the identity matrix, then this actually the rejection rates are of order delta t to the power 3/2. So introducing this D term here makes it so that you actually drop, you lower this rejection rate. And this you cannot, well, we tried actually to make I don't know, choose one specific diffusion coefficient that makes up that makes it such that we gain this order back, right? But we have not succeeded. So we tried to actually go into this Hamiltonian Monte Carlo setting. So this is a bit, we change the setting basically. We do not work on this overdamped Langevin dynamics anymore, but much more on this Langevin process. And we ensure that using this Hamiltonian and this kind, for example, the general Ashton-Moore-Verlet or the implicit midpoint rule numerical schemes, that actually in position, we are very close to the overdamped Langevin dynamics.
But I mean, sorry.
But yeah, indeed, the fact that you're introducing the diffusion coefficient is costly. I mean, it's a cost that you have to make sure that in the end you do not reject so much. Mm-hmm. And this is why we try to go into this Hamiltonian Monte Carlo setting to actually gain this order back.
I mean, that's a similar question, isn't it? Because I mean, basically, when you go to the Hamiltonian setting, you're changing the mass matrix of your system, right? And that makes it non-separable. But I mean, I have some intuition why the Bayesian approach is meaningful, because you're basically trying to make the sampling isotropic. I guess this is what happens when you're using the inverse of the Hessian. But it's not so clear to me why e to the plus beta v helps you in this case.
Yeah, this one. So yeah, this is a work that actually my supervisor, both of my supervisors are actually working on right now. Is that in a way, in a 1D periodic setting, so on the torus, in a way this can be seen to be like an optimal diffusion coefficient, like in a homogenized limit. This is not so clear. I cannot really explain because it's their work, but yeah, it's some work has been done so that actually this has also been said in the Robert-Stramer paper, and well, this form is actually can make, maybe I can show this. Okay, in 1D, for example, this form actually cancels this term. If you take exponential beta v here, this whole term actually goes to 0 in 1D. And so that you're still left with only the noise. And if you take this noise, then you simply suppress the drift term and you actually use only the noise that you have. And in a way, you suppress the fact that you may have some problems. Actually, this drift term makes you go very far away to not where you want to go. And so you only keep the noise. And because you have the choice for D, maybe you're going into the right direction.
Mm-hmm.
So yeah, but in theory, it's more like in a continuous setting. In the homogenized limit, in a way, this can be seen as an optimal diffusion coefficient. So I guess, yeah, looking at this Robert-Stramer article, or maybe waiting for the preparatory work that they are doing right now. Yeah, it's some calculations. It's like a optimal in the terms of this Euler-Lagrange equations, and when you're doing that, and sorry, it's optimal in a way of a larger spectral gap, so of your operator, right? So you want to actually make sure that your eigenvalue is as large as possible.
Mm-hmm. Okay, yeah, thanks.
Thank you. Actually, there is a comment from Gabriel Stolz building on the question by Burkhard, but probably it's better if you can explain it yourself rather than me.
Yeah, sorry. Sorry to interrupt, Regis, but a quick comment about Karsten's question as well is that so for this homogenized limit, what we do is that it's a 1D thing. We take a potential, we repeat it a lot of time in the unit cell, and so in this homogenized limit, we have some effective Brownian motion with some diffusion coefficient, and the microscopic diffusion matrix D of Q, which maximizes this somewhat macroscopic diffusion coefficient, is proportional to exponential beta V. I mean, it's just a miracle computation we can do, and that's our motivation, because after that, we are somehow interested in 1D, and that's the transition to Burkhardt's question, because we have in mind to do things at the free energy level, because of course exponential beta V when V is scaling as a number of particles is a terrible idea. That's going to be way too large. And so the idea would be to bias just by the free energy in order to have smaller quantities. And there my comment, Burkhardt, was that indeed we would do like the standard ABF or metadynamics methodology, where we would have a dynamics targeting not exponential minus V, but exponential minus V plus F, so something which is flat in the reaction coordinate. But instead of using like standard Langevin or standard overdamped Langevin to estimate the free energy, like in ABF or metadynamics, we would use, for instance, this modified overdamped Langevin dynamics with a D of Q, which would be proportional to exponential beta, the current estimate of the free energy. So we would be both playing with the dynamics and doing some important sampling in an attempt to combine the best of both worlds. Well, this was a comment.
Okay, thank you very much. I don't see any additional further questions, so thank you again, Regis. And now we can move to the last presentation of this first part of today's event. That's by Janine Scheer from the Johannes Gutenberg University in Mainz. So we're talking about passive particle in an active bath. Can we tell is out of equilibrium? So Janine, now the floor is yours.
Okay, thank you for this opportunity, and also thank you all for being here. Hopefully you can all see my screen now.
Yeah, we can.
Okay, great. Okay, so I'm a PhD student at Johannes Gutenberg University, and my advisor is Friederike Schmidt, and this is work that was also done with Gerhard Jung. And the research that I'll present to you today is on a passive particle immersed in an active bath, and specifically trying to answer the question of how can we tell that this system is out of equilibrium. So as you can tell by the title, I'm working with a system with active matter. And that's one specific type of non-equilibrium system. So active matter in general, an active matter system has some kind of constituents in it which propel themselves by adding energy to the system. And so that's what makes it inherently non-equilibrium. And this can happen on all kinds of different length scales, all the way from bacteria, all the way up to the level of humans and animals. And one of the things that's really interesting about active matter systems is that not only are the individual constituents of active matter systems different than passive systems, but also when they are together, then they can exhibit collective behavior. So you can get motility-induced phase separation, or for a macroscopic example, that's what we see when we see flocks of birds. That's a type of collective behavior for that particular type of active matter. And so the specific type of active matter system that I'll be talking about today is that of a passive particle, shown here by the red circle, immersed in an active bath, where all of the different active bath particles are shown by these blue circles. And the active bath particles, what they do is they propel themselves forward with a force that is constant in magnitude, but changes direction with normal rotational thermal diffusion. And I'll give you a more exact description of these particles a little bit later in the talk. But the main question that I want to ask about this system is, how can we tell, just from looking at the probe, whether we have an equilibrium or a non-equilibrium system? And previous studies on this particular system have shown that the behavior of the passive particle immersed in an active bath is very similar to that of an active particle itself. So in order to get a better idea of where to look for these non-equilibrium signatures, what I'm first going to do is take a look at the non-equilibrium signatures of an active particle itself. And specifically, I'm going to take a look at the non-equilibrium signatures of an isolated active Langevin particle, which then I will later use active Langevin particles in the full system, so in the active bath in which my probe is immersed. So active Langevin particles are just like active Brownian particles, except they have this inertial term here. In addition to this inertial term, they also have the propulsion force, which again is constant in magnitude, but changes direction with normal thermal rotational diffusion. And then these particles are also coupled to an implicit thermal bath, which is represented by some dissipative force and some stochastic force. And just by taking a look at the equations of motion for the isolated active Langevin particle, we already can see one non-equilibrium signature, which is given by the enhanced kinetic temperature, which you see in this equation here, which is comparing the kinetic temperature of the isolated active Langevin particle to the temperature of the thermal bath to which it is coupled. And you can see there's some enhancement here, which indicates it's out of equilibrium. But one thing that's a little bit difficult about this non-equilibrium signature is that in order to detect it, you have to know something about the bath to which your active Langevin particle is coupled, and that's not always feasible. So we're going to continue looking for some more non-equilibrium signatures of this particle, which we can detect just by taking a look at its trajectory. So in particular, we're going to take a look at the velocity distribution of the isolated active Langevin particle. And that's what you see in this main graph here. And just as information for in general looking at my graphs, whenever I'm showing different active forces seen in this legend here, then the equilibrium system will always be shown by this purple line, and then the furthest from equilibrium, so the highest active force, will always be shown by this orange line here. So the velocity distribution of the isolated active Langevin particle from simulation data is shown by the solid line in this graph. And then the dotted line, what that shows is the approximate solution for the velocity distribution of the isolated active Langevin particle, which we can derive from the Fokker-Planck equation. And you can see that the simulation data fits very well to this approximate solution. So we'll take a look at what this solution tells us. So you can see this first term here, that's just a Gaussian distribution, which is exactly what we would expect for an equilibrium passive particle. But then in addition, we find this cinch term here, which we would not expect in an equilibrium system. So this is a non-equilibrium signature that we see in our velocity distribution. And we try to give a more quantitative feel to this non-equilibrium signature by looking at the relative entropy between the simulation data for the velocity distribution and a Gaussian distribution with the same standard deviation, which is what you see in this inlaid graph here. And you can see that for low active forces, the distribution remains pretty Gaussian. So this term here is dominating. But then as you get to higher and higher active forces, then it drifts further and further away from a Gaussian velocity distribution. So this term begins to dominate, and that's a non-equilibrium signature. So we've already seen for the isolated active Langevin particle that we have two non-equilibrium signatures. First of all, we see an enhanced kinetic temperature, which we can detect if we have information about the bath to which the active Langevin particle is coupled. And second, we have a non-Gaussian velocity distribution, which is a non-equilibrium signature that we can detect just by looking at the trajectory of the particle. So now we're going to take this information and bring it back to take a look at the overall system, which is that of an immersed passive particle in an active bath. So again, the active bath particles, those are the active Langevin particles that we had before, except now they're not isolated. Instead, they're interacting both with each other as well as with the probe immersed in the bath. The probe immersed in the bath is only being governed by its interactions with the active Langevin particle bath. So it is not coupled to the thermal bath. And now what I'm going to do is look at the same things that I did for the active Langevin particle to see if I see the same or at least similar non-equilibrium signatures in the trajectory of the immersed passive probe. So I start by looking at the velocity distribution, which you see here in this left-hand graph. And here what we have, the solid line again shows the simulation data for the velocity distribution, but this time the dashed line shows a Gaussian distribution with the same standard deviation. And you can see that these curves match each other really well. So even when the bath in which the probe is immersed becomes active, you still see a Gaussian velocity distribution. So you can't, which is indistinguishable from equilibrium. And in order to get a better idea of how close these distributions are, we took a look at the relative entropy between these two distributions in this inlay here. And what you can see from this graph is, first of all, the relative entropy is very small, on the order of magnitude of 10 to the -4. And also there really aren't any systematics in the relative entropy. And so because of that, we can really say that the probe maintains a Gaussian velocity distribution even when it is immersed in an active bath. So this can't serve as a non-equilibrium signature. The probe does, however, exhibit a enhanced kinetic temperature, just as the active bath particle, which you can see in this graph here. So we determine the kinetic temperature by just taking a look at the mean squared velocity here. And then what you see in this graph is the difference in the kinetic temperature of the probe and the kinetic temperature of the active Langevin particle bath. And you can see that when we're at equilibrium, this is 0, as we would expect, because we would expect the the probe to equilibrate to the same kinetic temperature as the active Langevin particle bath. But as we get further and further away from equilibrium, so increasing the active force, then we see that this difference grows, even continually grows. And what we actually see is that there are actually two levels of a lack of thermalization. So first of all, the active Langevin particle bath does not equilibrate to the same kinetic temperature as the thermal bath to which it is coupled. So then that's one layer of lack of thermalization. And then we see another with the probe, where we see that it also does not equilibrate to the same kinetic temperature as the active Langevin particle bath in which it is immersed. So this enhanced kinetic temperature can serve as a non-equilibrium signature, but again, it requires knowing information about the bath to which the probe is coupled, which is not always feasible. Unfortunately, we can't see a non-equilibrium signature in the velocity distribution of the probe because this remains Gaussian and so is indistinguishable from equilibrium. And therefore, in order to try to diagnose a non-equilibrium signature, which we can get just from the trajectory of the probe, what we next do is we map the motion of the probe onto the generalized Langevin equation, which this is very helpful that Tanya already explained this, so I don't have to do as much here. But so what we're doing is we're mapping the motion of the probe onto this equation. And recall that the motion of the probe is just governed by its interactions with the active Langevin particle bath. And then essentially what we're doing in mapping it to the generalized Langevin equation is that we're taking the forces that are exerted on the probe and dividing it into a dissipative force and a stochastic force. And here I am not assuming that the dissipative force is Markovian, so I have this memory kernel term in here. And I calculate the memory kernel term by using the inverse Volterra equation, which is given here. And as Tanya said earlier, when you are using a linear projection operator, then what you get is you get a second fluctuation dissipation theorem, which relates your stochastic noise to your dissipative interactions. And that's given by this relation here, where in this case, with using the observable of velocity, then you have the autocorrelation function of the stochastic noise will be related to the dissipative interactions, which are embedded in the memory kernel. And previous studies of this system have claimed that the second fluctuation dissipation theorem will be broken for the probe in this system. So what we did was we decided to check this violation of the second fluctuation dissipation theorem, or in general to test the second fluctuation dissipation theorem, which is what we do in this graph here, where you see in the solid line, you see the memory kernel, and then in the dashed line, you see the stochastic force autocorrelation function, which is scaled to get rid of this prefactor. And you can see that in equilibrium, they match exactly, which is what we would expect in equilibrium, but we also see that they match even when the bath is active. So, and we tested this for many different active forces, which is what you see here in this inlay, where you have on the y-axis, you have the memory kernel, and on the x-axis, you have the scaled stochastic force autocorrelation function. So we find that the second fluctuation dissipation theorem for the system is actually fulfilled. And what has actually been shown in this paper here is that the second fluctuation dissipation theorem will always be fulfilled as long as you are using certain definitions for your memory kernel and for your stochastic force. So this means that this is indistinguishable from equilibrium. So we can't use the violation of the second fluctuation dissipation theorem as a non-equilibrium signature. We do, however, see that the shape of the memory kernel changes in the active bath. You see this negative portion developing here, but that is not inherent to non-equilibrium. So we can't really use this as a non-equilibrium signature. So therefore, we're going to go and test one other fluctuation dissipation theorem, which I'll refer to as the first fluctuation dissipation theorem, which relates the non-equilibrium response of a system to its equilibrium relaxation. And so the way that we do this is we add a perturbative force to the probe, which you see here, and then we look at its non-equilibrium response and compare it to the equilibrium relaxation, namely the velocity autocorrelation function, which then that's what you see in this graph here. So on the y-axis, you have the non-equilibrium response, and on the x-axis, you have the velocity autocorrelation function. And so what you would expect to see if the first fluctuation dissipation theorem is fulfilled is you expect to see just a straight diagonal line across this graph, which is indeed what we see for equilibrium. But as we increase the active force, we see that that is no longer the case. We no longer have a straight diagonal line. So we're seeing that the first fluctuation dissipation theorem is being violated in this case, and it's increasingly violated as we move up in activity for the active bath. And we show a specific example for that right here, where we show in the solid line, we show the velocity autocorrelation function, and in the dashed line, we show the non-equilibrium response. So we can actually use the first fluctuation dissipation theorem as a non-equilibrium signature for the probe, which we can detect by just looking at the probe's trajectory. So what I've shown you today is that the non-equilibrium signatures of a probe immersed in an active bath are harder to detect than those of just an active particle itself. While an active particle itself develops a non-Gaussian velocity distribution at high activities, this is not the case for a probe immersed in an active bath. The probe maintains a Gaussian distribution even when the bath in which it is immersed is active. We can, for both an active particle and the immersed probe, detect an enhanced kinetic temperature, but in order to do this, we have to have information about the bath to which the particle is coupled, which isn't always feasible. So if you want to find a non-equilibrium signature for the probe immersed in an active bath, just by looking at its trajectory, then what you need to do is add a slight perturbation to the probe and then test the first fluctuation dissipation theorem. And in the case that the system is out of equilibrium, then you will find a signature through violation of the first fluctuation dissipation theorem, which you can just get by looking at the trajectory of the probe. And with that, I would like to thank you for your attention, and I am open to any questions.
Okay, thank you very much, Janine, for the presentation. I remind once again that in this questions and discussion part of this associated to the talk, you can indicate simply in the Q&A channel your intention or interest to ask a question, and then we will unmute you and you can interact directly with Janine. So while we wait, as usual, I just had a question regarding to this, the second fluctuation dissipation. You said that that's based on this generalized Langemann equation, and there are generic situations why it is not violated because of the relationship between the kernel and the noise. It's not clear to me whether you claim that this is universal or this is a particular subset of functions, and then this particular system will always obey them.
So it's whenever you make a certain definition for the memory kernel and for the stochastic force, it's generally true. So essentially, whenever you use this inverse Volterra equation here to define your memory kernel, which is what we do in our system or in our data set, is you will get a fulfillment of the second fluctuation dissipation theorem. You can define the memory kernel and stochastic force so it would be violated, but whenever you use this definition here, it inherently will not be violated.
Okay, but this then presumes a particular choice for the noise. That's what you mean?
Yes, then because once you choose this memory kernel, then the way that you determine the noise is just essentially a trivial rewriting of the generalized Langevin equation where you put this on the other side. And so then it ultimately determining the memory kernel through this method will then determine your stochastic force.
Okay. Thank you. So there is a question by Felix.
Hello, I have one question connecting to this discussion before about the potential of mean force. What happens if we put in a confining potential to the probe particle? So there are several questions that one can ask. One is, if we look at the distribution of the positions of this probe, this should be some kind of Boltzmann distribution with some temperature. What do we expect? Would this temperature match this effective bath temperature, for example?
I think it would, one, depend on the potential, but I believe in a harmonic potential, I believe the two will end up matching if you, or I can't, do they? I don't think, okay, let me rephrase it. I don't think, I'm not entirely sure. There has been research done on this type of particle confined in a harmonic potential. I don't think I've seen much work on it in other potentials. And I know that, I believe that it equilibrates to the same, I'm not sure then if it equilibrates to the same temperature as the active bath in that case, because also they use, the articles that I have seen have used different definitions for memory kernel and stochastic force. And so I am not entirely sure in that regard.
Yeah, so but the distribution in the end would be independent of the definition of memory kernels, and so because this is a stationary.
Yeah. Yeah.
The other question, of course, is could we say get insight into these nonlinear Langevin equations with nonlinear memory with such a relatively simple but still non-trivial system?
Yeah, so that I'm not sure, and I was also kind of questioning that after the end of Tanya's talk. I was wondering if we could get insight into that. I haven't looked into the nonlinear generalized Langevin equation for this system.
Okay.
Perhaps it's an idea for.
Yeah, definitely.
Yeah.
I was also thinking about how this could be relevant to after Tanya's talk.
Thank you.
Thank you very much. There is now a question by Burkhard.
Yeah, well, thank you. Nice talk, Janine. So your very last successful test that relied upon essentially checking linear response theory. Yeah.
Mm-hmm. Yeah.
And linear response theory, of course, relies on assuming that the external driving is sort of infinitesimally weak, or sort of not much stronger than thermal fluctuations. Yeah.
Yeah.
And that may be when you do numerics, maybe a tricky business. So that you have to carefully check whether your driving is really small enough, or whether you are perhaps already in some sort of nonlinear regime, which would then not be a true hallmark of non-equilibrium. I mean, have you done tests in this direction?
So no, I don't think so. So I mean, I guess then I would ask a question back, just asking, so in what sense wouldn't this be a non-equilibrium response? Are you meaning the perturbation would be?
Yeah, I mean,
okay.
I mean the alpha of t. If that amplitude is too large, you run into trouble, I think. Right?
Okay.
Yeah.
I mean, I don't think we did intensive testing of that, but I mean, we saw that in equilibrium, it was returning the first fluctuation dissipation. It was fulfilling the first fluctuation dissipation theorem. So, and it's the same perturbation that we're adding to each of them. So
yeah, sure, but I mean the quote unquote the susceptibility or the sensitivity to the external driving might depend in a quite non-trivial fashion on this F0.
Yeah, okay. Yeah, so that we have not checked. It's a very small force, but that's a good point that we should check that.
Okay, thank you.
Okay, thank you very much. There is no additional questions. Well, there is a question by Aurelien Pereira asking what is the link to the YouTube versions of this SICAM event. So if you go to the YouTube and you type the SICAM channel, then there we have all the this one in particular, and also all other videos associated to this series. You can also access them through the SICAM website. If you go to the MixedGen events page, then there also there is the same information through our webpage, so you can access it both ways. It takes a couple of days to have everything ready, so this session should be available beginning of next week, typically. Yeah. Okay, so thank you very much, Janine, for the presentation and for the discussions. And thank you for all of you to stay here with us. Just to finish, if you can stop. Yeah, perfect. Thank you, Janine, because then I wanted to, as usual, end up with a couple of slides where essentially I thank you all for having joined us. And I remind you that for those who have registered, now you can join us on Gather Town for the second part of the event, where we have the poster session and the more open discussions in the room. So you should have received the link by email to access there. And as I was mentioning, previous sessions are available. Here I give you the link through the SICAM website, just typing MixedGen, or through YouTube. I hope that you have enjoyed, you have found it useful, can disseminate around, and that stay in tune for our future activities. Remember, if you register to our webinars mailing list, then you will receive emails regularly, also in Twitter. And thank you very much again.